goes as mass cube. Okay. Sorry. Goes like. Okay, there are several convenient ways in which we can rewrite this. Okay, for example, one of the convenient way is to express this through the entropy, okay, of a black hole. And so this is then you can get the following structure. Okay, I can just rewrite this manipulating with h is L Planck square times Rg. Now this is an entropy, so this means that this black hole lifetime is proportional to the entropy in the size units. Okay. Now this immediately is telling you that whenever you are in semi-classical limits, okay, L Planck is 0, okay, R is fixed, L Planck is 0, so the lifetime of a black hole is infinity, okay, or which is the same, and from here you can see it immediately that again the black hole is proportional to the mass cube, right? This is another way to see it. So when mass goes to infinity, of course the lifetime goes to infinity, despite the fact that the size is finite. So in this regime, so therefore, let's summarize what we understand in these regimes. We understand that in these regimes, both classical and semi-classical, there is no mystery. Okay, semi-classically, you have an object which has arbitrary mass, but it's eternal. It's not radiating. Semi-classically, you have an object which is radiating, but again it's eternal because it's infinitely heavy. Okay. In both of these limits, everything is fine. You can store an infinite amount of information in this type of black hole. You will never get it back, but there is no problem because the black hole is also eternal. Okay, just store it eternally in the black hole. Now, the seeming puzzle or the question, let me even not call it puzzle, but sometimes it's called, as you know, information paradox. It's coming once you try to make black hole mass finite. In other words, you want to go into a fully quantum theory. Okay. Now, if I make black hole mass finite, then the whole question is what the observer sees, okay? How the spectrum of radiation of a finite mass black hole, but finite mass means that it's fully quantum, is modified relative to the ideal thermal spectrum, okay? So this is the key question. Now, without knowing answer to this question, of course, we can improvise infinitely. Okay, somebody will say corrections are negligible, somebody else will say no, corrections are important, and so on, right? But if we don't know how big are the corrections, we cannot conclude anything about any inconsistency or anything about any paradox or anything like that. Okay? So this is extremely important to understand what is the correction to the spectrum for a real black hole. Okay? Now the question is, how can we answer this question? What is the correction to the spectrum of a real black hole? Because this correction cannot be semi-classical. Why? Because in semi-classical theory, we don't have a correction. It has to be an intrinsically quantum correction. Now, therefore, to answer the question, okay, what is the underlying physics of this correction, or even how strong it is, we need a microscopic theory of a black hole. Okay? So you need to make some, in physics, normally what do? We make some assumptions, right? We say, okay, I have a postulate that this is how it should be. Then we go ahead and we try to check self-consistency of this postulate, okay? First we try to check whether this postulate reproduces everything we know, okay, correctly, in the limits that we know. Then we press on and see what it predicts. Sometimes it may predict a nonsense. Then we say, okay, we close this chapter because this postulate is inconsistent. Okay, this is how it works. So we need some initial input, a theory which will tell us what is the constituency or what is the substructure of a black hole. Okay? Now, this theory could be, you may like it, somebody may like it, somebody not like it. The postulate may look complicated, may look simple. It may be wrong even, or right. But that's a secondary point because you need something to start with. Otherwise, you cannot answer the question. Okay? You need a framework. Okay, so therefore, what I will try to do, I will try to describe a framework, but what I will try to do, I will try to do it in extremely general terms, okay? So that there is a huge room for improvisation if you want to fine-tune the details, okay? Just to separate what is secondary, what can be technicalities or some fine-tuning of the framework, and what are the major postulates that you cannot avoid. Okay? This is the question. So, therefore, I will ask the following question. The question is very simple. Do black holes have substructure, or are they elementary? Okay? Now, as I just explained in the language of elementary particles, right? Elementarity doesn't mean that the object cannot have a size. You can very nicely have the arbitrarily big size of an object, but object could still continue to be elementary. Okay? So the question is whether black holes have any substructure, whether they have some composite nature, but composite nature in a well-defined sense. Okay? Now, before trying to answer this question, we have to understand what do we mean under compositeness. When I tell you that, okay, I'm asking whether black hole is composite, what do I mean? I mean, what I'm looking for. Okay? Why? Why this is an important question? Because you can tell me, for example, why do I care if black hole is composite or not? For me, it's enough that black hole, there is some quantum state in some Hilbert space, okay, of quantum gravity. Yeah. Yeah, the question will show us the way, okay? So far, we're asking, that's why I'm saying, let's be extremely general and open-minded, okay? So not to miss any opportunity at any turn, okay? So far, now, as you see, what I'm trying to do now, I'm even trying to understand what is the question that I'm asking, okay? Right? So just to make clear. Why? Because you can always tell me, why do I need substructure? Give me some vector, some space vector, and that's a vector in the Hilbert space, okay? What do you mean when you say elementary? Simply, this, whatever you call elementary or composite, is just some state in my Hilbert space. Okay, so now you can ask exactly the same question about any other entity. For example, this table. Okay? It's the same thing, right? We can say, of course, this table, for me, I can say that this table is described by a quantum state in the Hilbert space. Okay? Very nice quantum state, a table. Okay? And why do I care if it's elementary or composite? But nevertheless, we care, right? When we say table, nobody thinks in the right mind that table is elementary, right? Despite the fact that it's a fully legitimate quantum state, okay? So, now, that means that there is something about these entities that are composites which makes us think that it's better to think about them as composites than to think about them as elementary. It's a question of convenience, okay? Now, question of convenience in physics is very important because question of convenience allows you to solve very hard problems, right? Precisely by going into convenient language and convenient description, this is the half of the job, right? You have to find the appropriate description for a given problem. Now, so when we say that the table is elementary, there is